Hi, everybody. So now I want to talk about an example of a very deep idea which is important in machine learning and statistics generally, and that's the idea of Bayesian inference. This is, in some sense, a philosophy of statistical reasoning which has become quite influential. But even if we leave aside some of the philosophical arguments about it, it's still very useful in concrete situations. And at its heart is Bayes' theorem, but it takes a little bit of setting up. So let's take a look. So the basic idea behind Bayesian inference is that you start with a statistical model of some phenomenon that you're interested in. And that statistical model has a group of parameters that control it. And in the Bayesian world, the assumption is you can't ever exactly know these parameters. You can only have a statistical notion of these parameters. So for each parameter, you have a probability distribution, which is based initially on your prior sense of the world. So that's called a prior distribution. And an example of such a thing might be, if I tell you with no other information that it's a cold day, meaning that it's a winter day in Connecticut, and it's about 11 o'clock in the morning, and I ask you what the temperature is, you're going to tell me, well, it's probably cold. Maybe it's 30 degrees, but it might be somewhere between, say, 20 and 50 degrees, and more likely towards 30, something like that. That's a prior distribution on one of the parameters of a statistical model where the underlying parameter is the true temperature. Now, the next step in Bayesian inference is that you do an experiment. And for example, you go outside and you measure the temperature. And then, having measured the temperature, perhaps several times using a thermometer, which also has some error in its measurements, you collect the data and you combine it with your prior distribution, and you use those things together to update your knowledge of the world. And the result is a new distribution on the temperature called the posterior distribution, which tells you, in light of the data that you collected, what is a better sense of the range of temperature. So if your measurements of the temperature are all around 40, instead of having a probability distribution that tells you that it's likely 30 degrees, but maybe between 20 and 50, in light of your measurements of temperature in the 40-degree range, you might now say that the temperature is probably around 40, and maybe it's between 35 and 45, given the error in your thermometer. That's the process of Bayesian inference. And it's close to the way people think about how science works. And so that makes it appealing in a lot of scientific experiments. So once again, here's your example. You have a thermometer that reports the true temperature up to a normally distributed error. So that's a statistical model. You have a prior sense that the external temperature is around 30 degrees. That's your prior distribution. Around means there's a probability distribution around 30. You make a bunch of independent measurements. Let's say they're scattered around 40 degrees. And then you update your prior distribution in light of this data and conclude that the temperature is probably closer to 40 degrees within some range of error. Now we want to try to make this process precise. And to do that, we're going to use Bayes' theorem. This process of updating your prior is driven by Bayes' theorem. So remember what Bayes' theorem says. Here you can think of T and D as just any events in a sample space. And it says that the probability of T given D is the probability of D given T times the probability of T divided by the probability of D. This is just a restatement of Bayes' theorem. But now what we're going to do is we're going to interpret this in a particular way. On the left-hand side, we have the probability of T given D. So here, T is going to be the temperature in our particular example. And D is going to be the data from our experiment. So it's going to be a bunch of measurements using our thermometer. T is somehow the true temperature. The thing on the left, the probability of the temperature given the data, is what we're trying to figure out. It's asking us, in light of our experiment and our prior, what is the distribution of the temperatures that we should be using? So this is called the posterior distribution. The probability of d given t is the chance that, as a function of the temperature using our statistical model, how likely are we to have observed the data that we observed? So we saw this in our discussion earlier of maximum likelihood estimation. We can ask if we assume that the temperature is normally distributed and we make a bunch of measurements, we can ask how likely are those measurements as a function of the temperature and the variance. And that's called the likelihood of the data. P of t is our initial or prior sense of the distribution of the temperature. So we have to choose that as part of this process. And the denominator is the total probability of our data for any possible temperatures. And this is typically a very hard number to compute and also typically not necessary, because on the left we have a probability distribution in t. And so we know that there has to be a normalizing constant to make our thing come out to have integral 1. And oftentimes we can dodge around what that constant actually is. So often we ignore this. It's a normalizing constant. And a lot of Bayesian techniques are basically designed to avoid having to compute that integral, which is typically very complicated. Now we look at a specific case. So we're using our temperature model, and there are two parameters in our temperature model. There's the true temperature outside, T star, and there's the variance of the errors in measurement of the temperature. And the probability density that we're using is the normal distribution shifted to be, you can think of this either as saying we're shifting it so that the peak of the normal distribution is at T star, which is the true temperature, or you can think of this as a distribution on the errors. T minus T star is the measurement error as a function of t. And so you can think of this as a likelihood of a particular error, as we saw earlier. And in this case, we don't know T star or sigma squared. All we can do is go out with our thermometer and make n measurements to get a bunch of temperatures, T1 up to Tn. And we want to now update our prior distribution in light of this data. And as we'll see, in the case that we're looking at here, it's possible to do this whole process analytically because we've chosen things in a careful way. So now we go back to Bayes' theorem and we plug in the various ingredients that we have. So the left-hand side, the posterior distribution, is the probability distribution of T star and sigma squared, the temperature and the variance, once we have done our experiment and collected our data. So this is what we're looking for, the posterior distribution. The probability that t equals t0 given T star and sigma squared is, if you fix a value for T star and sigma squared, it's how likely are your n measurements to have yielded T1 up to Tn. So that's the likelihood as we did in the maximum likelihood estimate. And it depends on the values of T star and sigma squared. The probability of T star sigma squared is the prior distribution. It's our initial impression of what the likely values of T star and sigma squared is. And finally, the denominator, the total probability, is this big integral over all possible values of T star and sigma squared. But we're just going to, as we'll see, not worry about that. It comes out in the end. So we don't have to do that nasty integral. And now we're going to work through this numerically, but we're going to simplify the situation. We're going to assume that the variance of the measurement variance, the variance of our thermometer is 1. So we're going to reduce the number of unknowns in this problem by 1. Maybe not realistic, but it'll make our lives a lot easier in the following calculation. So somehow or other we know that our thermometer that we're using to measure the temperature reports the true value with a variance, but it's off. It's within the true value by a normal distribution with variance 1. So the only remaining unknown is the true temperature T star. And Bayesian inference isn't going to give us T star. It's only going to give us a distribution of values that T star is likely to have. That's in contrast to maximum likelihood, where we could go through maximum likelihood and we would get the most likely value for T star. In some ways that makes you feel better because you get an actual number, but you've thrown away a lot of information that Bayesian inference preserves. Okay, so let's pull together our ingredients. First, we have the prior distribution. So we assume that the average temperature is 30 degrees because it's a cold winter's day in Connecticut, but we have a lot of range for it to vary. We allow a variance of 15 degrees, which, as you can see from this diagram, means that the temperature is really between 0 and 60 with a pretty strong peak at 30. And there's a lot of choices for priors, and there's a whole art and practice to choosing them. It's for the calculation we're going to do, it's important that we choose a normal distribution, and this seems as reasonable as any. And the formula for this normal distribution is given by 1 over the square root of 30 pi e to the minus t squared minus 30 squared over 30. And so that's what we're going to use in Bayes' theorem. For the likelihood of the data, we've done this before as well. We're making n independent measurements from our thermometer, and our thermometer has the property that the error, the probability of getting a t minus t star equal to x, is e to the minus x squared over 2, 1 over square root of 2 pi. Because it's a normal distribution with variance 1, but if you're going to do that n times, then by independence, the probability becomes the product of 1 over square root of 2 pi e to the minus xi squared over 2, which is 1 over square root of 2 pi to the n e to the minus the sum xi squared over 2. And we can simplify that a little bit by writing that as a vector where that t, the norm of t0 minus t star e squared, is the norm of the vector t1 minus t star, t2 minus t star, and so on, which is the sum of ti minus t star squared, the norm squared. So this is the probability distribution of our measurements, T1 up to Tn, the likelihood of having gotten those depending on what the true temperature is. If we were going to do maximum likelihood estimation, we would now maximize find the value of T star, which made our particular measurements most likely. And if you did that, you would find that T star should be the average value of the T's. And the total probability is the denominator. We're just going to call this T and move on because we're going to try to avoid having to compute it. So if we take all the constants in Bayes' theorem, which remember Bayes' theorem said that the posterior distribution is the likelihood times the prior divided by the total probability. And each of these things is this and this are, the top numerator are both normal distributions, and they have constants in front of them involving square root of 2 pi and so forth. And the bottom has a constant and is a constant. And we're just going to package them all together and call that constant A, and focus our attention on just the exponential terms in probability of d given t and probability of t. And that gives us, since we're multiplying exponentials, we add the exponents, and we get this quadratic term in the exponent. And if we pull that exponent out and call it q, it's looks like this. And this looks kind of messy, but the only variable here is t star. The ti's are constants. So this is just a quadratic polynomial in t star. It's, I don't know, a t star squared plus b t star plus c. And those constants are a mess, but I've done the algebra for you, and if you are willing to believe me, then you can actually complete the square and write this as t star minus u squared over 2v plus a constant, where u is given by this formula, 2 plus the sum of I ti over 1/15 plus n, and v is 1 over 1/15 plus n. Remember, n is the number of measurements. And if you use those variables and you go back up to where they came from, which is here, what you find is that the posterior density is itself a normal distribution, centered at U with variance V. And there's some constant in the front, which we still are avoiding computing, except that because this is a normal distribution and it has to have total integral 1, we could figure out what B is, because it has to be the case that if you integrate this from negative infinity to infinity, T star, you have to get 1. So B is some 1 over square root of 2 pi something or other. It still doesn't matter. We're not going to care, because it's enough to know that it's a normal distribution centered at U with variance V. Finally, we go outside with our thermometer and we make some measurements. And we measure temperatures of 40, 41, 39, 37, and 44. So N is 5. There are 5 measurements. The mean of them is 40.2. And the variance of them, the mean squared error, is 5.4. If you plug those numbers back into the formulas for U and V, what you get is that U is 40.1 and V is 0.2. This number U is called the posterior mean because the posterior distribution is a normal distribution and its mean, or its center, is at U. And this is called the posterior variance. It's the variance of the posterior distribution. And if we plot these, here's a graph that has both the prior and the posterior on it. If I clear out some of the underbrush here, the prior in this scale is this very spread out red curve at the bottom, which measures the, down here. Remember, our prior said the temperature was 30, but it could have been anywhere really between 20 and 60. The posterior is now what we think should be the case after our measurements, and you see it's very sharply peaked at 40.1 with a very small base at the bottom. So we've learned a lot from our experiment. We've learned that the temperature is very close to 40.1 with only a little bit of error at the bottom. And that's the posterior distribution. If you look at these formulas for U and V a little bit more closely, you'll notice that if we had made lots of measurements, if n went to infinity, that the limit as n goes to infinity of U is actually the sum of Ti over n. And the limit as n goes to infinity of V is 0. So if we made more and more and more and more measurements, this posterior peak would move closer and closer and closer to the average of the measurements, and the width of the peak would shrink to 0. The other comment I wanted to make is you'll notice that the posterior mean is ever so slightly less than the sample mean, which is just the mean of the observations. And that's the effect of the prior. The prior tells us that we kind of more expected the temperature to be closer to 30 than 40. And so when we do this Bayesian process of updating our prior in light of the data, that little bit of residual prior information causes us to shift the interpretation of our data a little bit down towards 30. And as we saw, that effect becomes smaller if you make more and more measurements. In situations where you make relatively few measurements, the prior has a bigger effect. And in fact, it can be thought of as a way to smooth out the variation that's brought in by errors in measurements. So in political polling models, you often have priors based on how regions voted in the past or the demographics of a region, which help to smooth out the big margins of error that you get from public opinion polling. Of course, they still have a lot of problems with it, but a lot of these Bayesian techniques are used in political opinion polling. So to wrap up this rather long discussion, I wanted to give a general result because I simplified some formulas, and it turns out that if we did this calculation again with some more parameters in it, we would get a nice answer. So what I want to assume now is that our measurements, our thermometer, if you want to think about it, gives measurements that are normally distributed around a true value mu with a fixed known variance of sigma squared. So in our case, mu was 30 and sigma squared was, mu is unknown. It's the temperature. And sigma squared was 1. This is what we assumed about our measurement error. And for the prior distribution, suppose that our prior distribution has mean mu 0 and variance tau squared. So in our case, mu 0 was 30 and tau squared was 30. This was our tau squared was 15. And that was our prior distribution. So if you go through the whole calculation that I just did with the completing the square and all that other stuff, what you get is that the posterior distribution is again normal with variance tau prime squared and posterior mean, but kind of a weighted average of the sample mean, which is y bar, and the prior mean, which is mu 0. So we saw this, that the prior mean influences the sample mean a little bit. But as n goes to infinity, that effect becomes smaller and smaller. So if you redid this calculation, but you had slightly different values, you could still do this computation. But the underlying fact that the posterior is again normal, this is because it's a special property of the normal distribution. We chose a normal prior and a normal measurement model, and we got out of that a posterior, which is also normal. So that's a lot to assimilate, and I think I will stop there.